What's up, Calc 2 crew, and welcome back to the Daily Problem Sets. And today we're going to take a look at polar coordinate system. Again, remember you should have already watched the lecture video on this material. We'll just take a look at a couple more examples. With polar coordinate system, we have some nice identities that we like to use with this. I like to work with x is r cosine theta, y is r sine theta, and then we also have x squared plus y squared equals r squared. There are other identities involving tangent and how to find theta. I think those can be sometimes a bit more trouble than they're worth, and I think these identities actually suffice for what we're going to need to be doing in our polar coordinate system. But let's take a look at the example that we have here. Find the Cartesian coordinates of the given polar coordinate point, and then we just want to plot the point. We can actually get some nice insight this way. Since I'm given the polar point, it is important to know that that would be given r first and then theta second, so r comma theta is our polar point, and we'd like to get another ordered pair x comma y to represent this. So right away, I actually know a couple things that are important. I know that r is 2, and that theta is 3 pi over 2. Well, now all I really have to do to find x and y, and it's actually not so bad going from polar coordinates to Cartesian coordinates, is I can actually just plug in directly. We say x is going to be r times cosine theta, so that's 2 times cosine of 3 pi over 2, or that's 2 times 0, which gives us 0. And that y is going to be r times sine theta, so that's 2 times sine of 3 pi over 2, or that's 2 times negative 1, which is negative 2. So this polar point that we had, 2 comma 3 pi over 2, I can think of this in a Cartesian coordinate system as the point 0 comma minus 2, x comma y. And if I were to plot this point, I can actually make a good deal of sense about what the polar point is achieving. Say if I just had my x and y axes, then my point in a Cartesian system, this is very familiar to us, 0 comma minus 2, would just be along the y-axis down 2 units. We'd say if I was describing this in a polar coordinate system, we'd say, okay, well, the angle would be 3 pi over 2. And that makes sense, right? Since I'm actually right in between quadrants 3 and 4, we would sort of think of these axes as, if I'm moving in positive or negative x direction, and same with the y direction, we would say 0, pi over 2, pi, and then 3 pi over 2. And then all the way, a full revolution would bring us back to 0. We would consider it to be 2 pi then. But 3 pi over 2 is actually straight down in the y direction. So it makes sense. And then we're also saying that the radius is 2, meaning that I'm just a distance of 2 away from, I guess we consider it the origin, but in a polar coordinate system, we'd call it the pole. We are 2 units away. So this one's actually pretty nice to confirm what we've done. We do have a good Cartesian representation. We have this extra space here, so I'll write a little note to you. You are the best. Yes, you. Put a smiley face in there too. Well, okay, let's talk about going in the other direction. Here I'm given the Cartesian coordinate point. I want to find the polar coordinate version of this. And I'm trying to make a restriction where r is positive and that theta is between 0 and 2 pi. So let's go ahead and take a look at this. We can go ahead and start by saying what we know. We know x is 3 and y is 3 times square root of 3. We'd like to find the polar point, so I want r comma theta. Now we have this nice identity to work with right away, that x squared plus y squared is equal to r squared. And so, okay, well, let's square what we have and sum it. So that would be 3 squared plus 3 times square root of 3 squared, which what would this be equal to? Well, 3 squared is 9 plus here I get 9 times 3, or that this is really 9 times 4, which is 36. So I get that r squared is equal to 36. If we think about this, though, there's actually two values that would work for r. Since we're first doing this restriction where r is positive, where r is greater than 0, we would say, well, okay, so it's one that we're probably thinking of first, that r would be 6, just taking the principal square root. As soon as I have r, I can actually start working with those identities for sine and cosine. Remember, x is r cosine theta, and that y is r sine theta. And I know what r is, and I know what x and y are. We have x is 3, so here I get 3 equals 6 times cosine theta, since r is 6, and y was 3 times square root 3, and that's equal to 6 times sine theta. And I would prefer to work with these two identities together than working with some inverse tangent function or anything like that, because I want to find a value for theta that satisfies both of these, and then I don't have to worry about which branch of tangent I'm working in. So I'd say, well, let me go ahead and divide both sides by 6. 3 divided by 6 gives me 1/2 is cosine theta. If I divide by 6 over here, I'm going to get 3 radical 3 over 6, or that reduces to radical 3 over 2 for sine theta. And thinking about these together, I want to find a value for theta where it's going to give me cosine of theta is 1/2, but also give me sine of theta is radical 3 over 2. Go ahead, pause the video, think about it a bit, let me know what you're thinking. Hey, welcome back. What did you get for theta? Hopefully you got pi over 3. It's got to be pi over 3. You need cosine to fall from 1 to rad 3 over 2 to rad 2 over 2 to 1/2. That's the last stop along the way, which is pi over 3. Similarly, we need sine to crawl up from 0 to 1/2 to radical 2 over 2 to radical 3 over 2. That's going to be pi over 3. So now we have our polar point. We found r and theta. So this would be 6, comma, pi over 3 would be the corresponding polar point. However, there is another. We could now take a look at, we could talk about if r is negative. If r is negative, we can actually go back to what we said about r squared earlier. We had a bit of a crossroads there. R squared is 36. There's another value that would work for r. Not just positive 6, but also negative 6. And we can go back through those same equations. We could say, well, x was 3, and now this is equal to negative 6 times cosine theta. And y was 3 square root 3, and now this is equal to negative 6 times sine theta. And solving each of these, we would say, okay, well, negative 1/2 is cosine theta. And then here, negative radical 3 over 2 is sine theta. And now we're really talking about some reference angle, really. And we're thinking about cosine and sine both being negative, so that means we have to be somewhere in quadrant 3. And say, well, we can then find this. There's actually sort of a nice, quick way we could do this. Since r is negative, we could actually think of this as a 180-degree rotation. But if you're actually solving both of these together, no harm, no difference there. You'd be able to find it this way as well. Let's say, well, this would have to be theta is equal to 4 pi over 3. So something in quadrant 3, but with pi over 3 as a reference angle. So this would be theta's 4 pi over 3, which would give us another polar point where r is negative 6, and theta is 4 pi over 3. So we have these two different polar points that we could rely on to give us the same sort of idea, the same location as to where this Cartesian coordinate point is, 3 comma 3 radical 3. Let's talk a bit about differentiation. Here I want to find the slope of the tangent line to the given polar curve at the point specified by the value for theta. We're given r is 1 plus 2 cosine theta, and then theta is pi over 3, which we just got done talking a bit about. If I want to differentiate when working with a polar description, it's a bit different. But I can use what we talked about earlier in parametric equations to help out. So we have x is equal to r times cosine theta, and y is equal to r times sine theta. And we remember our definition from parametric curves that I could write dy dx, and if theta is my parameter, I could write this as dy d theta divided by dx d theta. But there's another very important piece of information that I want you to keep in mind. I don't want you to overlook this, that r is a function of theta. And if you're thinking, well, why is that? Look at the example we're about to do. R can be expressed as a function of theta. So when I go to differentiate these x and y, I want to remember that r also is a function of theta, or certainly can be. And so I should be using product rule. So I'd say, well, okay, let's find dy d theta and divide it by dx d theta. We have to use product rule when we do this. So first, if I differentiate r, it has some derivative. It likely is a function of theta, so its derivative should be dr d theta, or r prime, however you want to consider that. And then I would rewrite sine theta. And then I would add to this and do the opposite. Now I'm just going to rewrite r times the derivative of sine theta is cosine theta. And now in the denominator, I want to do the same thing, but with x. I want product rule. I can first differentiate r, gives me dr d theta. And then cosine theta comes along. And then I can add to this. Now I can rewrite r times the derivative of cosine theta, which is negative sine theta. So that sign flips in between. So this is actually the formula that we would use in order to find our first order derivative when working with polar coordinates. And I have all the pieces that I need except for one piece. I do need to find dr d theta. So over to the side here, I'll say, well, let me find dr d theta. R is 1 plus 2 cosine theta, so derivative of 1 is 0, so we skip over that. Derivative of 2 cosine theta, 2 comes along. Derivative of cosine theta gives me negative sine theta. So we get minus 2 sine theta for dr d theta. But now I'm ready to just plug everything in to this formula that I've built. So we'd say, okay, well then dy dx is equal to, I want dr d theta first, that's negative 2 sine theta times sine theta, plus r is 1 plus 2 cosine theta times cosine theta, and then divided by dr d theta again is negative 2 sine theta times cosine theta, and then minus r, and r is this. I got to keep it in parentheses, treat it like it's one thing. 1 plus 2 cosine theta, and then times sine theta. Now what I want to do from here to find the slope of the tangent line is just to evaluate for theta equals pi over 3. So we'd say the slope then is dy dx evaluated at theta is pi over 3. So everywhere I see a theta, I'm going to plug in pi over 3. Now I'm not going to write that out. It would just be the same thing, but everywhere we see theta, pi over 3 is what the input is. But instead, I can start working through this. Now over here to the side, I'm just going to remind myself what we said earlier. We said cosine of pi over 3 is 1/2, and sine of pi over 3 is radical 3 over 2. And that's essentially what I'm going to be working with at the end of it. So here we'll say, all right, well, let's start plugging things in. So negative 2 times sine at pi over 3, that should be negative 2 times radical 3 over 2. And then times another sine of pi over 3, so times radical 3 over 2. And then plus, in parentheses, I have 1 plus 2 times cosine at pi over 3 is 1/2. Close my parentheses, and then multiply by another. Cosine at pi over 3 is 1/2. And then divided by, here I have negative 2 times sine theta, so that's negative 2 times sine at pi over 3, which is radical 3 over 2, times cosine at pi over 3, which is 1/2, and then minus, in my parentheses, I want 1 plus 2 times cosine at pi over 3 is 1/2, times sine at pi over 3, which is radical 3 over 2. And hey, we're doing it. Let's keep working through this. I can try to reduce a bit, simplify where I can. 2 of the 2's are going to cancel, the one on top and one of the ones on bottom. I have this minus sign left over. Radical 3 times radical 3 is 3 over 2 plus, here I have 1 plus 2 times 1/2 is 1. 1 plus 1 gives me 2 times 1/2. And then divided by, let's look in the denominator. 2 on top is going to cancel with one of the 2's on bottom. I have negative radical 3 times 1, which is negative radical 3, and then divided by 2. And then I have minus, here I have 2 times 1/2 is 1, 1 plus 1 is 2. So I have 2 times radical 3 over 2. And I see some more opportunities where I can cancel. I'm actually going to resist the urge to do that because right now I kind of have common denominators on top and bottom. So I'd say, well, negative 3/2 plus 2/2 is going to give me negative 1/2 divided by, on the bottom, negative square root 3 minus 2 square root 3 gives me negative 3 square root 3 divided by 2. And we'd say, well, don't divide a fraction by a fraction, instead multiply by the reciprocal. So here we would do negative 1/2 times, we have negative 2 divided by 3 radical 3. And the double minus sign is going to resolve to plus. The 2 over 2 is going to cancel. So I get 1 over 3 radical 3, which we would then say, you know, maybe let's rationalize it. So we'd get rid of the square roots in the denominator by multiplying by radical 3 over radical 3, just a clever form of the number 1. So it's going to still be the same number, but it's going to look a bit nicer to us as civilized people. We would say 1 times square root 3 on top gives us square root 3, divided by, in the bottom, I have 3 times, and then radical 3 times radical 3 gives me 3. So we'd write this as square root 3 divided by 9. And this would be the slope of a tangent line, as described in our polar coordinate system. All right, we're going to go ahead and take a look at 10.4 next, but that's it for 10.3. We're going to talk about graphing these polar curves, and we're going to talk about area with them as well. All right, we're here to take a look at section 10.4 now. We're talking about areas and lengths in polar coordinates. And let me start with the formula. To find the area of some polar region, the area is given by, we want the integral from a to b, some bounding on the region. We want 1/2 our function r squared d theta. Remember, r is a function of theta, so you could also write this as the integral from a to b of 1/2. Keeping in mind that r is some function of theta, you could say f of theta squared with respect to theta. I usually just use r because that's what we call the function in most of our usual notations. So we want to sketch the curve r equals 2 minus sine theta and find the area that it encloses for this first example. Now to sketch it, here's what I like to do. I like to go ahead and build a table of values for theta and then find corresponding values for r, where r is 2 minus sine theta. And unless there's something inside the trig function affecting the argument, I usually like to go by a generic scale of pi divided by 4. Is that the only way to do it? No. You can work with Cartesian graphs and graph polar graphs from Cartesian versions. I like to set it up this way though, and I would usually go by the same scale, unless it was something like sine of 2 theta or sine of 3 theta, sine of 4 theta, then I would have to change it. But let me go ahead and work with my scale. I'm going to start at 0, and then I'm going to do pi over 4, 2 pi over 4, which is pi over 2, 3 pi over 4, 4 pi over 4, which is pi. Need some more room here. 5 pi over 4, 6 pi over 4, which is 3 pi over 2, 7 pi over 4, and then almost done. One more would be 8 pi over 4, which is 2 pi. I just want to go up to 2 pi, and my scale is by pi over 4. And I'm setting up my table. Now you can fill them all out sort of in order. I would maybe jump around to the easiest ones first, just get them out of the way. We know that sine 0 is 0, so here I get 2 minus 0, which gives me 2. But also that sine pi is 0, which gives me 2 minus 0, which is 2. And also that sine 2 pi is 0. So I get 2 for all of those values. And then maybe the next nicer values would be pi over 2 and 3 pi over 2. We know that sine pi over 2 is 1, so I get 2 minus 1 gives me 1. And at 3 pi over 2, I get negative 1, so 2 minus negative 1, which is 2 plus 1, gives me 3. And then I just have pi over 4, and then anything with reference angle pi over 4 left. So here, if I were to plug pi over 4 in, sine at pi over 4 is radical 2 over 2. So I get 2 minus radical 2 over 2. And it should be the same at 3 pi over 4. If we remember, sine is positive in quadrants 1 and 2. And this also should give me 2 minus radical 2 over 2. But that in quadrants 3 and 4, the function sine is negative. So this would give me 2 minus negative radical 2 over 2. So that's going to be 2 plus radical 2 over 2. Same here at 7 pi over 4. Now these as exact values are wonderful, but difficult to work with, difficult to graph. So I would want to know what they look like with some sort of decimal approximation. And I would say to keep in mind that square root of 2 is about 1.4, roughly. So then radical 2 divided by 2 is about 0.7. And I'd go here and I'd say, well, let me see if I can get an approximation. This is about 2 minus 0.7, which is about 1.3. And then again. And then 2 plus about 0.7 is about 2.7. So I get these rough approximations of what I'm looking at. Now I'm ready to see if I can build my graph. Now to do this, you want to either have polar graph paper, or if you're like me, you're going to have to make your own. So I'm going to make my own polar graph paper. I'm going to start with my main axes. And then what I'm going to want to do is I'm going to want to cut through what would have been quadrants 1 and 3 diagonally, and through what would have been quadrants 2 and 4 diagonally. Let's see if I can do this as best as I can. It's not going to be perfect, but it's hopefully going to be good enough for our rough sketch. Like that. And then I want to pay attention. I want to pay attention to what is happening with R. So at its, well, sort of looking through the table values, I don't have every bit of information, but for what I'm going to be plotting, it looks like the largest it goes up to is 3, positive 3. So I'm going to create 3 concentric circles. Oops, well that's not quite what I want, so I'll get rid of that. Still getting used to this. Okay, I think this should be what I was hoping for. So that'll be a circle of radius 1, and then I want a circle outside of that. And this will be like my circle of radius 2, and then a circle outside of that. And this will be like my circle of radius 3. And again, not really doing anything too crazy here. Trying to get it as best as I can. And I would go around and I would label. Make sure I'm on the drawing tool. This would be 0. And this would be pi over 4. This would be pi over 2. This would be 3 pi over 4. This would be pi. This would be 5 pi over 4. Straight down, and I could have pulled this, dragged it down a bit further, but, you know, I didn't. 3 pi over 2, and this would give me 7 pi over 4, and if I make that full revolution, this would also be 2 pi over here. Now what I want to do with my polar graphs is I want to plot points in order, and I want to connect with smooth curves as I go along. These are sinusoidal functions, so they should be very flowy, nice, curvy. So I want to plot these points and connect with smooth curves along the way. We're saying when theta is 0, r is 2. If I remember my scale, I said this closest circle is circle of radius 1, then of radius 2, then of radius 3. So at 0, I should have 2. So here at 0 radians, I should have 2, so right here. And nothing to connect to yet, so I just plot that first point. But then at pi over 4, I have about 1.3, and I have to kind of guesstimate where this is, somewhere between 1 and 2, closer to 1. So that's about where 1.3 is, and I can connect with a smooth curve. And then at pi over 2, it should give me 1, so this innermost circle, I want to connect to that. And the graph isn't going to be perfect, but it's going to be good enough for what I'm using it for. And then at 3 pi over 4 should be about 1.3 again, so about there. And then at pi, we have 2. So here at pi, I should have a point at 2, and that's this the middle circle, right? Connect to it with a smooth curve. 5 pi over 4 is about 2.7, so somewhere between 2 and 3, perhaps a bit closer to 3, so about there, and I can plot it and I connect with a smooth curve. At 3 pi over 2, I should have a value of 3, which is this outermost circle. My line didn't quite come down far enough, but I still know where it should be. I connect to that with a smooth curve. At 7 pi over 4 should be about 2.7. So I can get a rough idea as to where that looks. Connect to it. And then it brings me to 2 pi, and 2 pi is at 2, which is really the same point that I started at. I can just connect back safely to it. And this gives me my rough sketch. Now this didn't really turn out exactly how it should look perfectly if I was using some polar graphing utility. It should look sort of like a shallow heart, right? We consider it to be a cardioid. And if I want to try to get an idea as to how it looks a little bit better, I can try to sort of shade in. Probably won't spend too much time doing this though, because it will take up a lot of time doing it, especially with the stylus. But it's this region here, kind of looks like a polar blob. I don't mind doing this though. You know, I always wanted to go to art school to be an artist. But I didn't. But this is my way to kind of have my cake and eat it too. Happy little polar blobs. Happy polar graphs. I think there should be a cloud here. Let's do a cloud in red. Happy cloud. I think there should be another tree here. Let's do a tree. And we'll just shade it all in. So this is my polar looking region that I have. There it is. Looks crazy, looks awesome, very aesthetically pleasing with these polar graphs. Now I'd like to find the area inside of it. Now we have this formula that we were talking about earlier, right? This integration of 1/2 our function r squared over its region. Now this blob goes and sort of continues this journey from 0 to 2 pi. So for this particular example, and we'll see some others that maybe aren't quite the same, I just want to integrate starting at 0 and ending at 2 pi all the way around to find all of the area. So we'd say setting up to find the area that I would want to integrate from 0 to 2 pi, and then it's 1/2 and then r squared, and r should be my function, and I was given the function r, where here r is 2 minus sine theta. So r squared should be 2 minus sine theta squared. And I can go ahead and FOIL this out. So we'll say the integral from 0 to 2 pi. Here I have 1/2. 2 times 2 gives me 4. I get minus 2 sine theta. Another minus 2 sine theta is minus 4 sine theta. Negative sine times negative sine is plus sine squared. D theta. And here I can go ahead and distribute my 1/2 in. So say, well, this is the integral from 0 to 2 pi of 1/2 times 4 is 2, and then I get minus 2 sine theta And then plus, I have 1/2 times sine squared theta, d theta. But now to integrate sine squared, I need to use a trig identity. So we'll say, okay, 0 to 2 pi, 2 minus 2 sine theta is ready to go. And I have plus 1/2. But then sine squared, I can use the identity that this is 1/2 quantity 1 minus cosine 2 theta. And then I might just clean this up one more bit. Well, let me actually integrate, and I'll clean this up. While I'm integrating, I am going to write 1/2 times 1/2 as 1/4, because it's 1/4. So let's go ahead and integrate, though, otherwise. So if I integrate 2 with respect to theta, it gives me 2 theta. And then here, minus 2 comes along. When we integrate sine of theta, it gives us negative cosine theta. So negative cosine theta is going to flip the sign. And then plus, we said this is 1/4. And then here in the parentheses, if I integrate 1 with respect to theta, it gives me theta. And then minus, if we integrate cosine, it gives me sine. Since it's cosine of 2 theta, it should be sine of 2 theta, and then divided by 2. And we either remember that, or we can actually get it with a very small substitution, letting u be 2 theta. And that's from 0 to 2 pi. Remember, we can check our antiderivative by differentiating, by taking the derivative, to make sure it returns us back to where we were. And now I should be ready to evaluate. So we say plug in the upper bound of 2 pi, plug in the lower bound of 0, and subtract in between. When I plug in 2 pi, I get 2 times 2 pi, plus 2 times cosine at 2 pi, plus 1/4 quantity, 2 pi minus sine 4 pi over 2. Then I want to subtract away from this what I get when I plug in 0, which is 2 times 0, plus 2 times cosine at 0, plus 1/4 quantity 0 minus sine at 0 over 2. And I should be able to work through this as much as I can. So what is this? Well, okay. In the first set of parentheses, 2 times 2 pi is 4 pi, plus cosine at 2 pi is 1. 2 times 1 gives me 2. Plus 1/4 times, in this other set of parentheses, I have 2 pi minus sine at 4 pi is 0. 0 divided by 2 is 0. So that's what I get for the upper bound being plugged in. And then minus, now for the lower bound plugged in, 2 times 0 gives me 0. Cosine at 0 is 1. 2 times 1 gives me 2. And then for all the rest of this, notice I have 0, which is 0. Sine at 0 is 0. 0 minus 0 is 0. 1/4 times 0 is 0. So all the rest is 0 anyways. And let's start unraveling, see what we got. So I have 4 pi plus 2, plus here 2 pi divided by 4 is 1/2 pi. And then I have minus 2. We'll say, well, the 2 minus 2 is going to cancel. So I'm left with 4 pi plus 1/2 pi. Get a common denominator, right? That's what we're here for. 4 pi is 8 pi over 2 plus 1/2 pi, and that's going to give me 9 pi over 2. So if you were looking at this polar region, this blob here that I shaded in, did the best I could, and you're thinking, well, what is the area inside of that? I'm happy to tell you, it's 9 pi over 2. So if you guessed that, you are correct. We'll take a look at a couple more examples. These can be lengthy examples because not only are we doing the graphing associated, then we're also setting up an integral and then integrating. So we're just going to take a look at the setup only for 2 more examples, and that's going to be it for us. But I want to find the area of the region enclosed by the inner loop of the curve r equals 2 plus 4 sine theta. I'm going to want to get my table. And again, I can use my scale that I've already been using, which is by pi over 4. And that should work well in this application as well. Let's say 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, 2 pi. Now I want to go ahead and fill out my table. And again, you can go through everything in order. I like to just sort of do the easiest ones first, sort of go through it strategically. Doesn't matter. Does it matter? No, doesn't matter. Sine at 0 is 0, so I get 2 plus 4 times 0, which just gives me 2. Sine at pi is the same, 2 plus 4 times 0, which is 2. And at 2 pi is the same. 2 plus 4 times 0, which is 2 plus 0, which gives me 2. Now sine at pi over 2 is 1, so that gives me 2 plus 4, which is 6. And sine at 3 pi over 2 is negative 1. So that gives me 2 plus 4 times negative 1, or 2 minus 4, which is negative 2. So far so good. Got a lot of information already. I want to remember that sine at pi over 4 is radical 2 over 2. So that's 2 plus 4 times radical 2 over 2, which is 2 plus 2 radical 2. And it's going to be the same at 3 pi over 4, since sine is still positive there. But at 5 pi over 4, it's going to be negative. So this would be 2 plus 4 times negative radical 2 over 2, or that's going to give me 2 minus 2 radical 2. And that's the same as what I'm going to get at 7 pi over 4. And now I would just want to get some rough approximations for these to help out. If you remember what we said earlier, that square root 2 is about 1.4, and 2 times square root of 2 is about 2.8. So if I go here, I can use it to help me out, do some quick arithmetic. 2 plus about 2.8 is 4.8. Happens again here. And then 2 minus 2 radical 2, well, that's about 2 minus 2.8, so about negative 0.8. Again here. And we want to build from here our graph paper. Now, if you have polar graph paper, it's going to make things a lot easier. That would certainly be my preference. But I don't have it, so I'm going to build my own. I was using white before. I think that's going to look a little bit nicer for the contrast. So get my axes, and then we have to cut through diagonally. Yeah, let's do it. As best as we can. As best as we can. Doing it. Oh. No, thank you. Yeah. Sure, why not? And then I want my concentric circles. If I can do that. Now, if I look at this one, I'm going to maybe do this a bit differently to scale. Looks like the largest I go up to is 6. So I could do 6 concentric circles. That would be a lot, though. What I would prefer to do instead would be to have maybe 3 circles and say that each are radius 2. And you can do this however you'd like, but that sounds good to me. So I'll do this first sort of innermost circle. Let me sort of move it so it looks a little bit better centered. Do another one outside of that. Don't judge my circles, please. He is doing the best he can. And then, yeah, good. It's good enough. It's probably fine. And I'll just go ahead and label 0. Pi over 4, pi over 2, 3 pi over 4, this is pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and if I make it all the way around, that full journey should bring me to 2 pi. Now I want to plot these points and connect with a smooth curve. Remember I said I only have 3 circles. The circles have radius 2 for the innermost, radius 4, and then radius 6 is what I'm thinking for these. Now, where am I starting? When theta is 0, I got 2, so that's this closest circle. plot my point. And then at pi over 4, we have about 4.8, so 2, 4, and then, so it would be just a little bit above 4 at 4.8, connect with a smooth curve. At pi over 2, we have 6, which is the outermost circle, and I want to connect with a smooth curve to that. Continuing our journey. Then at 3 pi over 4, I'm back to 4.8. So about there. Connecting. At pi, we have 2, which is this innermost circle. Now, what happens next at 5 pi over 4 is we have a negative value for r. I like to think of this sort of like moonwalking. If I head towards 5 pi over 4 along this kind of ray that I have, I'm moving in the direction of positive r, from 0 to positive 2 to positive 4 to positive 6 is how I have this set up. If I need a negative value, that means I'm going to travel backwards, kind of like I'm moonwalking, which is cool to do. Traveling backwards through the pole out the other side. So it's going to look like I'm traveling along pi over 4. But what it really means is I'm traveling backwards away from 5 pi over 4. So I say, okay, so if I'm starting here all the way out at the end, here I am at 5 pi over 4. This is positive 6, positive 4, positive 2. Now I'm at 0. Now I'm in the negative territory. I want negative 0.8 would be somewhere around here. It would be negative 0.8 at 5 pi over 4. And I want to connect to it with a smooth curve, so like this. And we continue. Now next we have 3 pi over 2, and that should be negative 2. So 3 pi over 2, I'm sort of covering it with my face, but here's 3 pi over 2, and I want a negative value for r, so I have to travel backwards, like traveling through time. Backwards. Doing the moonwalk. But here I am at 3 pi over 2. If I travel backwards, here I am at positive 6, positive 4, positive 2. And then if I travel back through, we don't call it the origin, we call it the pole, out the other end, now I'm in the negative values. Negative 2 would be here. I connect to it with a smooth curve. And then now at 7 pi over 4, I want that negative 0.8 again. I can try to make it look somewhat symmetric as best as I can. Connect with a smooth curve. And then at 2 pi, I'm back to 2, which is actually this very first point that I plotted. So I just want to connect to it. And this is the polar graph that I get. Now we want to talk about, the question says, find the area of the region enclosed by the inner loop. Notice we have this outer region, call it the outer loop, and this inner region, call it the inner loop. Just for aesthetic purposes, I'm gonna fill in the outer loop, but this is not what we're going to be finding the area for our setup. We want to find the area of the inner loop, and I'm not going to shade in the inner loop. But I'm going to say it again, I'm shading in the outer loop. I think it makes the picture look a little bit nicer this way. The inner loop is not going to be shaded in, because I'm not shading it in, but we are going to be finding the area of the inner loop, which is going to be an unshaded part of it. You could shade the inner loop. Well, maybe I will shade the inner loop. I can do it in a different color. Doesn't that sound like a good compromise? So this is outer loop, sort of the complement. The inner loop, let's do that in the blue. The inner loop that we're going to find the area of is this region here. We want to find the area of that. Let's see if we can set up to find it. Let's think about what happens to sort of form the inner loop. And hey, inner loop, outer loop, if you're from Rochester, let me know in the comment section below. So what happens when I sort of graph this polar shape that I have here? I'm sort of going around, and then to start the inner loop, I had to cross through the pole. I had to go through 0, and then the inner loop starts. Whoa, exciting, inner loop, inner loop, inner loop. Do a kickflip, inner loop. But then to leave the inner loop, to exit the inner loop, I have to cross through 0 again. So to start the inner loop, I have to go through 0, and then it starts, and it's amazing, it's radical. But then to leave the inner loop, I have to go through 0 back out. And we can use that to our advantage. So to find the bounds here, where it's going to start, and where it's going to end, I should be crossing through 0 for all of that. So we say, well, set r equal to 0. 2 plus 4 sine theta equals 0. And if I go ahead and solve this, I'd say, okay, 4 sine theta is negative 2. Divide by 4, so sine theta is negative 1/2. This is what I'm trying to solve, and there should be 2 values for this. Now, I can tell you where sine of theta is positive 1/2. We would say, okay, sine of theta is positive 1/2 means that theta is going to be pi over 6. I want a reference angle to this. If you remember, sine is positive in quadrants 1 and 2, but negative in quadrants 3 and 4. So I'm looking for these other angles that have reference angle pi over 6. So I have reference angle pi over 6. And we can find those. To find the first, I would want pi plus pi over 6. To find the other one, I would want 2 pi minus pi over 6. I got to back away from it a bit. 2 pi minus pi over 6. And if I get common denominators and solve for these, I would get 7 pi over 6. And here I would get 11 pi over 6. And we can kind of cross-check a bit of our work here. We'd say if I'm going to cross through 0, it's got to happen here where r goes from positive to negative. So there should be some value between pi and 5 pi over 4. And to go back out through 0, it should happen when we go from negative to positive. We'd say, well, that's where these values live, right? We'd say between pi and 5 pi over 4 is where 7 pi over 6 is. Between 7 pi over 4 and 2 pi, well, that's where 11 pi over 6 is roughly. So these aren't crazy values, and we found them using reference angles. So now to set this up, we'd say, okay, if I just want the area of that inner loop, I should be integrating from 7 pi over 6 to 11 pi over 6. And I want 1/2 r squared with respect to theta. And here r is our 2 plus 4 sine theta. And then we'd want to go ahead and integrate. And that's our setup. Let's see if we can take a look at one more, just the setup only. I want to find the area of the region inside the first curve and outside the second curve. And we're going to go ahead and set up for our graph. And for my scale on theta, I'm going to do 0, pi over 4, pi over 2, my usual, right? 3 pi over 4. We'll do pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and then 2 pi. Now here, if I go and plug in, I would want to plug in maybe to the easier ones first. Get those kind of out of the way. Cosine at 0 is 1, so it gives me 14 times 1, which is 14. Cosine at pi is negative 1, so that gives me negative 14. And cosine at 2 pi is 1, so that gives me 14 times 1 is 14. Now cosine at pi over 2 is 0, 14 times 0 is 0, and also at 3 pi over 2. And that just leaves me with what's left over. Cosine at pi over 4 is radical 2 over 2, so that's 14 times radical 2 over 2, or that's 7 radical 2. But then at 3 pi over 4, it's going to be negative. So we'd say, okay, well, that's going to give me negative 7 radical 2. And then it's going to be negative at 5 pi over 4 as well. And then when we get to something in quadrant 4, that's where it's going to be positive again, so this will give me 7 radical 2. If you need help sort of talking about the trig stuff involved here, let me know. There's lots of cool mnemonic devices that can help out. And you can also sign up for my Trig Academy in the link in the description, the Trig Academy. So let's go ahead and take a look at some approximate values for these. Remember what we said, square root 2 is about 1.4. So 7 times square root 2 is about 9.8. It's somewhere, I think, a bit closer to 9.89. I want a decimal approximation that's a bit more reliable. This would be be about? Negative 9.89. Let's go ahead and get graphing then. I'm not going to bother with the other one. R equals 7 is just going to be a circle of radius 7, so that shouldn't be hopefully too tricky to navigate. But let's see what we can get going here. Get our graph paper set up. Now with this, I see R goes all the way up to 14. I could do 14 concentric circles. Instead though, that seems crazy, like a lot of work for me, I'm just going to do 2 concentric circles. We'll do one of radius 7, and then we'll do another one of radius 14. And I think that that should give us a good enough idea as to what's going on here. Now, if I go and graph this 14 cosine theta curve, we'd say, well, at 0, it should be 14, which is all the way out on that larger circle. At pi over 4, we have about 9.89, so maybe roughly like here. Connect with a smooth curve. At pi over 2, we have 0, so that's at the pole. And then next we would be at 3 pi over 4. This is negative 9.89. So I have to then travel backwards through it. So negative 9.89 is around here. Connect to it with a smooth curve. And at pi, we're at negative 14. So I have to travel backwards through to get to negative 14. Connect with a smooth curve. Now, I don't really need the rest of my table. If I went through the rest of these values and plotted them, it would just retrace the same curve. So in fact, I'm kind of done here. And then the other curve that we have, r equals 7, I'll do that in purple, is actually one of my markers here. It's this innermost circle that I have. Sort of trace along it roughly. This is r equals 7. In the yellow and now with purple accents. And the question is very deliberate in what it says. It says the area of the region that lies inside the first curve and outside the second curve. So the order that they're displayed does matter, right? It says I want it to be inside the first curve, so inside 14 cosine theta in red, but outside the purple. So I can actually shade this in a bit and get an idea as to how this region looks. Inside the first curve, outside the second. And I want you to notice that it gives me this very nice crescent moon shape. And this should be perfectly symmetrical. It maybe doesn't look perfectly symmetrical because I'm a human trying to do a rendition of it, but it should be perfectly symmetrical. Now, what I can do to make this a bit easier to set up to find the area that I want, and let me sort of redraw it a bit sort of, maybe kind of crudely, but to sort of illustrate what I'm saying, is I can use symmetry. Right? This should be symmetrical. And instead of finding the area of all of it in sort of a more organic way, I could say, well, let me find the area of the top half and double it. Right, so I'm just going to find this part, but then I'm going to double it. And that should work out really well. It should still give me the same area because it should be perfectly symmetrical. If I'm going to do it that way, that means that my starting bound should be 0. So let me actually leave some space for me to do some work. We're saying, okay, I'm going to double what I have. I'm going to have a starting bound of 0, but what should the upper bound be? Well, I'm going to want to integrate starting at 0 until where these curves intersect. I want to find where they intersect, where they end up meeting. To find where they intersect, I just have to set them equal to each other. I'll say, okay, so then I want to find where 14 cosine theta equals 7, and that would be when cosine theta is equal to 1/2. If we're familiar with our trig, that means theta would be pi over 3. So, and you can set it up to find a sort of a direct way to find the area. I think it's a bit more difficult. I think it's not going to be as rewarding. This is going to be a little bit nicer, that I can actually just find the top half from 0 to pi over 3 and then double it. So I'm already doubling it. I have my bound set up. Now I need to think about how I'm going to find the area. I need 1/2, and then I want r squared. But in this case, I have to be very careful because it's inside the first curve, but outside the second curve. So I could think about this as sort of two integrals, if that helps. I could say, well, inside the first curve, so I'm still going to want to double everything, but inside the first curve would be inside the 14 cosine theta. But then I'm going to want to subtract away from this. I'm going to want 1/2 r squared for the other curve, which is the 7. So 7 squared times 1/2 d theta. And this would work great as a setup. Maybe just a few parting words here before we jump on out. You can factor the 1/2 all the way out or distribute the 2 in, however you want to think about it. And that's going to cancel. And then you can actually write this as one integral. We could say 0 to pi over 3. We could say 14 cosine theta squared, and then minus 7 squared d theta. Remember this 2, if I distribute it in, or if I factor the 1/2 out, it's going to cancel the 2 times 1/2. So we get this for our setup. And from there, we want to square it, and we want to work through some trig identities to integrate, and then should be able to find that area of the region. And everything's already been doubled appropriately for us, so we're going to be able to get it just from the setup here. Hey, thank you so much for spending your time with me. I hope you're doing well out there. Let me know what questions you have for me. Make sure you're watching the lecture videos. Make sure you're taking a look at the homework. But otherwise, I hope you're doing great. Remember, no matter where you are and what you're doing, to keep learning, keep dreaming, and to always follow your heart, no matter what. And I'm going to see you next time. So don't you go anywhere. We're going to be back with more math. I'm going to have my cats helping out. We're going to talk about some really interesting stuff later on. So I'll see you. Thank you so much for your time.